Every year, over 900,000 aircraft engines are manufactured worldwide, hearts that push giants of the sky on journeys across continents. But have you ever wondered how this metal monster is born? One that operates in conditions of over 2,000 degrees and at speeds that could destroy any metal. Inside it, titanium bones, a nickel heart, and composite lungs. And then, technologies resembling alchemy, single crystals, vacuum casting, and 3D metal printing. But the main secret is not in how it's created, but what's hidden inside. Watch until the end, and you'll learn something that even Boeing engineers keep quiet about. The turbofan engines that push giants of the sky, like Boeing and Airbus planes, resemble something out of science fiction. However, they are a true embodiment of engineering genius. How are these amazing machines assembled from tens of thousands of parts and ingredients, like a puzzle? Ordinary metals are not suitable for their manufacture. After all, the engine must operate in conditions where the temperature can exceed 1,800 degrees Fahrenheit. This is a real inferno, and ordinary steel simply wouldn't withstand it. This is where titanium alloys come on stage. Lightweight, strong, and able to not melt in extreme heat. And for the hottest zones of the engine, nickel-based superalloys are used. By the way, this isn't just metal, it's 21st century alchemy. Composites, particularly carbon fibers, are used for the fan to reduce weight while maintaining strength. Such a high temperature arises from the process of burning fuel in the combustion chamber, one of the most important elements of a turbofan engine. During engine operation, aviation fuel, usually jet fuel, is mixed with air and ignites, forming hot gases. These gases are literally accelerated to insane speeds and temperatures, over 1,800 degrees Fahrenheit, and sometimes even up to 2,700 in modern engines. This level of heat is needed to get the most efficient thrust. That is, the hotter and faster the gases, the stronger the energy flow that spins the turbine and provides the aircraft's motion. And here lies the main challenge. The engine must not only withstand these extreme conditions, but also operate stably, without the slightest failure. That's why it uses super technological materials, like titanium alloys and special composites, which can withstand both high temperature and insane mechanical stress. You know what's incredible about the process of creating an engine? That even individual parts, like the turbine blades, are created with micron precision. For example, the blades are cast in a vacuum so that there isn't even the smallest crack inside. Some of them are formed to have a single crystal structure. That's when a piece of metal has no seams at all. But that's not all. 3D printing? Yes, that's used too. For example, for complex parts that are impossible to make with traditional casting. The turbine blades are the heart of the engine. They operate in the hottest zone and convert the energy of the hot gases into rotational motion. First, a model of the blade is created from wax. Yes, it looks almost like artistic sculpting, only here, precision down to the micron is important. This wax sample is then dipped into a special ceramic solution, which gradually dries, forming a strong mold. This mold is like a perfect cast of the future blade. The wax inside is melted and removed, and the ceramic is ready for the most important stage. Next, the show begins. In a special furnace, superalloys are melted, which include nickel, chromium, and other metals capable of withstanding temperatures above 2,000 degrees Fahrenheit. This molten metal is poured into the ceramic mold. But the secret is not only in the material, but also in the way it's done. To make the blade withstand gigantic temperatures and loads, it is often cast as a single crystal. This means that the entire piece of metal has no seams, microcracks, or different grains, as in ordinary metal. Why is this important? Seams or microcracks in such conditions are like a minefield. One mistake, and the blade shatters. Single crystals are grown through very slow cooling. The mold with the molten metal is gradually lowered into the cooling zone of the furnace. This process can take several days, but the result is a perfectly strong and durable blade. When the metal cools, the ceramic mold is broken, and the blade undergoes thorough grinding. A special heat-resistant coating may be applied to the surface so that it can withstand extreme temperatures even longer. And so, each blade is checked separately. If there is even the slightest defect, it doesn't go any further. Fuel injection nozzles, combustion chamber parts, or even compressor blades in aviation are made using 3D printing. For example, the company GE Aviation prints nozzles for its engines that weigh 25% less, but are 5 times stronger than traditional ones. Layer by layer, from powder and light, parts are created that allow planes to fly faster, farther, and more economically. First, engineers create a digital 3D model of the part with maximum precision. Here, every curved surface or cavity matters. Why? Because these parts often work in places where a millimeter can change everything, from the engine's efficiency to its reliability. The digital model becomes a map for the 3D printer, which knows where and how to create the required shape. Instead of the usual piece of metal, an ultrafine powder is used here. For example, of titanium, nickel, or Inconel, this is a superaluminum alloy. It looks like sand, but with particles so fine that they are almost invisible to the naked eye. The powder is poured into a special reservoir, and it becomes the building material. The principle of the printer's operation is simple but ingenious. It melts the powder using a laser or an electron beam. The laser heats the powder to such a temperature that it literally fuses into a homogeneous metal structure. Then the next layer of powder is applied, and the process is repeated. This method is called selective laser sintering or melting. And what's cool is that 3D printing allows for the creation of even the most complex geometric shapes. For example, parts with internal cooling channels, which are generally impossible to produce by casting or milling. You know, in traditional manufacturing, you often have to first make a large part and then cut off all the excess. This is not only time-consuming, but also expensive because a lot of material is wasted. But 3D printing works differently. Only what is needed is created without waste. The resulting part is not yet completely ready. After printing, it undergoes heat treatment. It is heated and gradually cooled to relieve internal stresses in the metal. Then comes the final grinding, polishing, or mechanical processing if precision needs to be adjusted. And of course, each part undergoes thorough testing. After all, everything here is serious. If a part does not withstand the load, the consequences can be catastrophic. The engine assembly takes place in a huge hangar, where every foot of space is occupied by tools, engine parts, and people in overalls who are intently working on something extraordinary. This place is the final stage of creating an aircraft engine. Here, individual parts, such as blades, compressors, combustion chambers, and casings, are transformed into a single whole, ready to lift an airplane into the sky. It all starts with the engine casing, which resembles a giant metal cylinder. This is the skeleton to which all other parts will be attached. The casing is made of titanium or nickel alloys, as it will have to withstand insane loads. Engineers work like watchmakers. The casing is secured in a huge machine tool to ensure everything is perfectly level. Next come the compressors, several rows of blades that are responsible for compressing the air before it is fed into the combustion chamber. The blades are installed one by one, as if decorating a giant wheel. Each one is checked by hand, as the slightest defect can ruin the entire job. After the compressors, it's the turbine's turn. These are the blades that convert the energy of hot gases into motion. The turbines are placed so precisely that the distance between the blades and the casing walls is sometimes measured in microns. Next, the combustion chamber is installed, the real hell of the engine. Here, compressed air is mixed with fuel and burned. Engineers install special nozzles that ensure a uniform fuel supply. And here, everything must be perfect. An incorrect nozzle angle, and the engine can lose efficiency or even fail. A central shaft runs through the entire engine, a kind of backbone. At one end of the shaft, a fan in the form of a huge wheel is attached to the front of the engine. At the other end, the turbine. When the turbine rotates under the influence of hot gases, the shaft transmits this energy to the fan, which sucks in air. Special robots are used to install the shaft. This part of the process requires surgical precision, as even a microscopic misalignment can cause vibrations that will kill the engine. When the internal part of the engine is assembled, the external systems are added. Fuel pipes that supply fuel to the combustion chamber, an oil system that provides lubrication for all moving parts, and electronics, because the engine is literally packed with sensors that monitor temperature, pressure, speed, and much more. These elements are attached using cables, tubes, and bolts that must withstand not only vibration, but also extreme temperatures. After the assembly is complete, the engine is not sent to the aircraft right away. First, it is attached to a test stand, where real flight conditions are simulated. From takeoff to turbulence at an altitude of almost 33,000 feet. This is the most spectacular stage. Starting the engine at full power is accompanied by a roar that can be heard for several miles and bright gas streams. The engine runs under load for hours, and engineers check it for strength, endurance, and efficiency. When the engine passes all tests, it is disassembled, the main components are checked again, and then it is finally assembled. The finished engine is packaged and transported to a Boeing or Airbus factory, where it becomes part of a new aircraft. And so, part by part, engineers create the heart of an airplane, which is capable of carrying thousands of passengers across continents. Isn't that a modern masterpiece? Let me know if you would like to see more videos like this. Every year, over 1 billion feet of steel chains are produced worldwide, from those that lift sea cranes to those that support bridges. But only a few of them go through a journey where precision is measured in microns, and every spark during welding is the beat of a metal heart. Imagine, a piece of ordinary steel transforms into a link capable of withstanding tens of tons. How exactly? In a few minutes, you will see how a force that cannot be broken is born. And if you watch until the end, you'll learn the secret that determines whether a chain will survive under maximum load. Our journey begins not in the noisy workshops, but much earlier, in the design office. It is here, at the design stage, that engineers determine what our chain will be like. What is it intended for? What loads must it withstand? Will it operate in an aggressive environment? The answers to these questions dictate the choice of material. In the vast majority of cases, for the manufacture of welded chains used in lifting mechanisms, industry, construction, or as fastening elements, we use high-quality steel rod. Take a look at these warehouses. Here they are, our round bars, thick, heavy, shining with strength. They can have different diameters, from a few millimeters for light chains to tens of centimeters for true giants that lift tons of cargo. Each batch of rods undergoes a thorough incoming inspection. The metallurgical laboratory checks the chemical composition of the steel, its mechanical properties, tensile strength, impact toughness. This is critically important, as the safety and reliability of the final product depend on the quality of the raw material. Only rods that meet the highest standards are allowed for further processing. This is the first, but extremely important, step in ensuring the unsurpassed quality of our chains. So, our selected steel rod is ready for transformation. The next stage is cutting. Here, high-precision cutting machines come into play, which, like surgeons, cut long rods into sections of a perfectly specified length. These sections will become our future links. Every millimeter matters, as the uniformity and correct geometry of the entire chain depend on the cutting accuracy. Operators carefully monitor the process, controlling the dimensions of each blank. And now we move on to one of the most spectacular stages: forming the link. Look at this powerful machine. It's an automatic press or a special bending unit. The metal section, heated to a plastic state, and sometimes without preheating if the diameter and steel grade allow, is fed inside, and under colossal pressure or a complex bending motion, it is transformed. Before our eyes, a straight rod is bent into a perfect oval or round shape, the future link. It is important that the ends of the rod are not completely joined, leaving a small gap, a seam. This seam will be a key element for the next stage. The newly formed link is fed to a mechanism that threads it through an existing link of the chain. It's like an amazing dance where one part is woven into another, creating a single whole. And now, the most important moment: welding. Most often, electric resistance welding, or flash butt welding, is used for chains. This is a high-tech process where the ends of the link that form the seam are clamped between electrodes. A powerful electric current is passed through them, which instantly heats the metal to its melting point. See those bright flashes? The fountains of sparks? That's the metal melting. And then under the pressure of the electrodes, an upset occurs. The ends are joined, forming a strong, homogeneous weld. In some cases, especially for very large chains, arc welding may be used, but the principle remains the same, creating an unbreakable metal joint. This weld is not just a connection. It's the weakest point of the link, and it is here that its future strength is established. Welding masters are true virtuosos, as the integrity of the entire chain depends on their work. After welding, the excess metal can be trimmed or processed for smoothness. The newly formed and welded chain, although strong, has not yet revealed its full potential. To meet the highest requirements for strength, durability, and safety, it goes through a series of finishing processes. The first of these is calibration. The long chain passes through special dies under pressure. This ensures the precise dimensions of each link, eliminates minor deformations after welding, and gives the chain uniformity. A calibrated chain will be ideal for working with sprockets and other mechanisms where precision is critical. After calibration, the chain heads to the heart of the factory: heat treatment. This stage is one of the most important and determines the final mechanical properties of the chain. Depending on the steel grade and desired characteristics, the chain may undergo several operations. Let's talk about each of them separately. Quenching. The chain is heated to a high temperature in special furnaces and then rapidly cooled in water, oil, or a polymer solution. This makes the steel very hard but brittle. Tempering. To eliminate the brittleness after quenching and increase the ability to absorb impact energy without breaking, the chain is heated again, but to a lower temperature and cooled slowly. This process gives the chain the necessary balance between hardness and ductility, normalizing. Sometimes, instead of, or in addition to, quenching and tempering, normalizing is used, heating to a certain temperature, followed by cooling in air. This improves the metal's structure and relieves internal stresses. All these processes are carefully controlled by computer systems, as even a small change in temperature or holding time can significantly affect the final result. Heat treatment is a true art of controlling the properties of metal. After heat treatment, the chain comes out of the furnace, but its journey is not yet over. At this stage, it may have scale on it, a layer of oxides formed at high temperatures. Therefore, the next step is cleaning. This usually happens in special shot blasting chambers. Thousands of small metal shot particles under high pressure bombard the surface of the chain, knocking off scale and other contaminants. The result? The chain becomes clean, smooth, with a pleasant metallic sheen, ready for the next stages. In order for our chain to serve long and reliably even in difficult conditions, it needs protection from corrosion. This is where coating comes into play. The most common method is galvanizing, which can be hot dip or electroplating. In hot dip galvanizing, the chain is immersed in a bath of molten zinc at a temperature of 860 degrees Fahrenheit. Zinc, interacting with steel, forms a strong protective coating that not only prevents rust, but also has the property of self-healing for minor damages. In electroplating, the chain is placed in an electrolytic solution, and under the action of an electric current, zinc deposits on the surface of the steel. This coating is thinner, but gives the chain a more aesthetic appearance. In addition to galvanizing, other types of coatings may be used. For example, polymer paints or special anti-corrosion compounds, depending on the purpose of the chain. We are approaching the final stage, and this is perhaps the most responsible moment: testing. It is here that our chain confirms its readiness to perform the most complex tasks. Every single chain undergoes a whole complex of checks for compliance with international safety and quality standards. Look at this huge test stand. Here the chain is subjected to colossal loads. It is stretched with a great force, which significantly exceeds its nominal working load, but at the same time does not reach the breaking point. This is the so-called proof load test. During this process, possible hidden defects and weak points that could manifest during operation are revealed. If the chain successfully passes this test, it means that it will withstand the declared loads and ensure safe operation. In addition to this, other types of control are carried out. Specialists carefully inspect each link for cracks, deformations, quality of welds, and coating. With the help of special calipers and measuring instruments, the compliance of the link sizes, their shape, and the chain pitch with the specified parameters is checked. From each batch of chains, samples are taken, which are then subjected to braking tests. This allows to determine the maximum braking force that the chain can withstand and to make sure that it meets or exceeds the established norms. These are brutal but necessary tests that guarantee that the entire batch of products is reliable. Only chains that have successfully passed all stages of quality control without exception are given the right to leave the factory premises. Each batch is accompanied by a certificate of conformity, which confirms its characteristics and the passing of all tests. This is our guarantee, a guarantee that you are getting a product of the highest quality and reliability. And now, dear viewers, we see the final result. Chains of different sizes, diameters, with different coatings, neatly laid in coils, ready to be sent to all corners of the world. They will go to the construction of skyscrapers, to port cranes, to ships, to agriculture, to production lines, everywhere where unbreakable strength, reliability, and safety are needed. From small, elegant chains for decorative purposes, to huge ones that lift bridges, each of them has gone through a long and complex path of transformation, from raw metal to a high-tech product. Every year, over 20 million tons of glass are recycled worldwide. But have you ever wondered what actually happens to the bottle you just tossed into the recycling bin? It's about to embark on a journey through fire of over 1,500 degrees Celsius, magnetic fields, and air currents, where even a tiny impurity can ruin everything. Glass is broken, sorted, melted, and then it's born again. Sometimes as the very same bottle. But that's not the most interesting part. Because at the end of this video, you'll learn the secret that every transparent wall hides, and it will change your perception of trash forever. So, how does a glass product get a new life? The recycling of bottles begins with the collection of used glass. In many cities and countries, there is a system of separate waste collection, which contributes to effective recycling. In many cities in different countries, special containers are installed for collecting glass, separate from containers for plastic, paper, and organic waste. This helps to prevent the mixing of glass with other materials, which simplifies the subsequent recycling process. But some countries or companies implement a system of glass collection points, where people can turn in used bottles and receive a reward for it. This stimulates the population to participate in the collection and return of glass bottles for recycling. In many countries of the former USSR, this collection is carried out by unprotected and marginalized segments of the population. But in EU countries, it's a daily practice for everyone to turn in used containers and receive, for example, a discount on their supermarket bill. The collected glass is sent to recycling plants, where the main processing begins. After the glass bottles are collected in containers or through collection points, they are transported to special sorting centers for further processing. The waste is collected by special garbage trucks that periodically empty the collected glass from the containers and transport it to sorting centers or directly to recycling plants. This is usually done on a large scale for more efficient transportation. Sorting by color is extremely important because different colors of glass are used for different products. Mixed colors can degrade the quality of new products. The bottles are sorted automatically. For this, special optical scanners are used that automatically recognize the color of the glass and sort it into clear, green, and brown. This is important because different types of glass require separate processing. The sorting machines are equipped with special sensors that identify the color of the glass using light sensors. Whole bottles or pieces of glass move on a conveyor belt, and the machines illuminate them with a lamp or laser. The light reflected from the glass is analyzed by sensors. The system determines the color of the glass about which a signal was received and sends a note about it to the controller. After color identification, each piece of glass is sent to the appropriate section, either by a stream of air or mechanically removed from the conveyor. The glass is divided into separate streams, which greatly simplifies further melting and use in new products. After sorting by color, the glass passes through magnets and air streams that remove metal elements, such as caps, as well as other impurities, paper labels, or plastic residues. Powerful magnets are installed on the conveyor line, which capture all metal impurities, including iron caps. And electromagnetic separators are used to remove aluminum caps and foil elements. Pneumatic removal is used to remove plastic and label residues from the conveyor. A powerful stream of air blows away the parts unnecessary for further glass recycling. And of course, the glass also undergoes wet cleaning in special washing systems, as many of these bottles will be used after recycling to create containers for food products. Just imagine, we throw away bottles as they are, and don't think about how much effort is needed for their further recycling. And compared to other materials, glass does not wear out or degrade during use. After sorting, the glass is crushed into a state of cullet, which is the raw material for the production of new glass products. For this, special machines are used to crush glass bottles into small pieces, which facilitates further processing. Crushers come in different types, but most are based on a mill with two parts, one of which is stationary, and the other is moving. The glass is simply ground during the friction of one part of the unit against the other. They can be jaw, cone, roller crushers, hammer mills. The glass is loaded into the crushing machine through a hopper or a conveyor belt. In the crusher, the material is processed by mechanical elements that reduce it to the required size. Some crushers may have several stages of crushing to achieve uniformity of particle size. At this stage, any residual impurities that were not removed during sorting can be further removed. After crushing, the cullet is sifted to remove particles that are too large, or conversely, too small. This is done to obtain a uniform mixture of cullet at the output, which is suitable for melting. New bottles or jars are most often melted from the fine cullet. It's a bit unsettling that they make new dishes from trash, isn't it? But powerful processing and high temperatures leave no chance for the glass to carry even a speck of something unpleasant into the finished product. After crushing, the cullet is cleaned of contaminants and undergoes additional processing before being sent to the melting furnaces with the help of magnetic separation. This process is used to remove any residual metals that may have remained after sorting. This is important, as even small metal impurities can negatively affect the glass melting process. Next, special technologies are used to remove residual organics, such as paper labels, adhesives, or other materials. This ensures that the cullet is completely clean before melting begins. Then the glass crumb is sent to vibrating screening machines, where it passes through screens of different sizes to be separated into fractions. Different coarseness is used for different products. The entire process at this stage is automated, and the machines are equipped with control and management systems. The use of specialized machines minimizes the risk of injury to workers during the processing of glass bottles, as the entire process is carried out in a protected environment. After cleaning, the cullet is sent to recycling plants, where it is transformed into a new glass mass. At the plant, the cullet is loaded into special furnaces, where it is melted at a temperature of 2,800 to 3,000 degrees Fahrenheit. The glass becomes liquid and ready for the formation of new products. Adding cullet to the melting process allows for reducing energy consumption, as recycled glass melts at a lower temperature than raw material. Adding new raw material, sometimes a certain amount of new raw material, sand, soda ash, limestone, is added to the melting process to maintain the chemical composition and quality of the glass. This helps to ensure the strength and transparency of new products. After the glass turns into a liquid mass, it is used for the production of new glass products. The liquid glass is directed into molds that create various products, for example, new glass bottles, jars, vases, or other glass containers. The bad part of the recycled glass is then used as a filler in concrete. This increases aesthetic appeal, strength, and improves thermal insulation. At large factories, this process is fully automated and can include high-precision molds to ensure the required quality and thickness of the glass. After forming, the glass products pass through special cooling systems, where the temperature is gradually lowered. This is important to prevent the formation of cracks and to ensure the mechanical strength of the products. After forming, the new glass products undergo strict quality control to ensure they meet safety and strength standards. For this, optical and mechanical tests are conducted. Special systems check the products for defects, such as air bubbles, cracks, or incorrect shape. If a product does not meet the standards, it is sent for reprocessing. Then the products are also tested for mechanical strength, especially when it comes to glass bottles that must withstand pressure and other loads during use. After all stages are completed, the new glass products are packaged and transported to the market for further use. At large factories, the packaging process is also automated. The glass products are grouped, packed in cardboard boxes, or on pallets for convenient transportation. The new products are sent to warehouses or directly to customers, beverage, food, and other goods manufacturers, where they will be used again, and the glass recycling cycle can begin anew. After all, this is a profitable and useful business. Glass recycling plays a significant role in reducing greenhouse gas emissions and water pollutants. By using recovered glass material to make jars and containers, humanity is able to minimize waste and reduce its carbon footprint. In addition, to make glass from scratch, a method of raw material extraction must be used, which does not have the best effect on the environment. Glass recycling has significant environmental benefits as it is energy efficient. The use of recycled glass, cullet, allows for reducing energy consumption for the production of new products, as melting cullet requires a lower temperature than melting raw material. Researchers on this issue indicate a 3% reduction in energy consumption. This also reduces the amount of waste in landfills. Glass is non-biodegradable in natural conditions and can remain in the environment for thousands of years, so its recycling is an important contribution to environmental preservation. Undoubtedly, recycling contributes to the conservation of natural resources. Glass recycling allows for reducing the use of natural raw materials, such as sand, soda ash, and limestone, which helps to preserve natural resources for future generations. Every year, over 400 million tons of paper are consumed worldwide. That's more than the weight of all the airplanes ever built by man. But have you ever wondered where this white sheet, on which we write, print, or package goods, comes from? It all begins with raw wood, which machines strip of its bark, shred into even chips, and send to giant boilers, where pressure and temperature transform the solid log into delicate cellulose fibers. This is not just production, it's the alchemy of modern times. And at the end of the video, I will reveal a secret that will change your perception of paper forever. The preparation of raw materials for paper production is a very important and interesting stage that lays the foundation for the quality of all the paper we later get. It begins with bringing the wood into a state convenient for further processing. First, large timber is delivered to the paper mill, where it is debarked. The reason is simple. The bark is not needed. It contains many impurities that spoil the quality of paper and create problems during cooking. To remove the bark, special machines, debarkers, are used. These are large rotating drums or hydraulic systems that, like real tigers, strip the bark from the wooden logs without damaging the wood itself. It's like a thorough scrub for the wood. The amount of bark can reach 15% of the log's weight, so removing it is not just necessary, but it also significantly improves the subsequent process and the final quality. After cleaning the wood from the bark, it is shredded into small pieces, which in the paper industry are called chips. Special mechanical chippers are used. These are machines with a large number of sharp knives that quickly and evenly cut the logs into small chips, approximately 1 and 2 inches long. It's like chopping firewood in half, only on a much smaller scale. It is important that the size of the chips is as uniform as possible. If the pieces are too large or uneven, then during the next stage, cellulose cooking, individual parts will be processed unevenly, which will affect the quality and strength of the paper. Therefore, the chippers are adjusted to maintain maximum stability of the chip size. Immediately after shredding, the chips are fed into cooking boilers. But before that, they are often moistened or slightly steamed to facilitate the softening and dissolution of wood components, such as lignin. These steps also improve the energy-saving characteristics of the process. One of the tricks is that the bark contains various minerals and substances that can contaminate the cellulose, create problems in chemical reactions, and disable the equipment. So, thorough cleaning helps not only to get a cleaned raw material, but also makes the cooking process more stable and of higher quality. Thus, how clean and strong the cellulose mass will be depends on the removal of the bark and the shredding of the wood. To make one medium-sized roll of paper, you need to process several hundred pounds of wood, so every step in the preparation is very important. After the wood in the form of chips enters the huge boilers, it is placed in special reactors, where it is boiled in an aqueous solution of a sulfuric lignin-removing alkali. Most often it is caustic soda and sodium sulfide. Usually, the cooking temperature reaches about 300 degrees Fahrenheit, and the pressure can exceed 15 atmospheres for the process to be effective. The chemical reagents dissolve lignin, the substance that glues the wood fibers together. At the same time, the wood fibers remain practically undamaged, which is important for the quality of the future paper. At the same time, other undesirable components that can affect the color, strength, and texture of the paper are also removed. This process is called sulfate, or craft cooking, and it ensures the production of the strongest and cleanest cellulose among all methods. For different types of paper, the proportions of chemical substances, the time, and the cooking temperature may differ, depending on the type of raw material and the required quality of the final product. After the cooking is complete, the cellulose suspension is cooled, washed to remove the remaining reagents, and sent for further cleaning, removal of residual impurities, and refining. To eliminate the foam that forms during this process, special defoamers are used. After cooking the cellulose, when most of the lignin has already been removed, the paper mass usually has a yellowish or brownish tint due to residual impurities. This is where the bleaching process comes into play. Bleaching is designed to make the cellulose white or as light as possible, which is especially important for printing paper, colored cardboard, or high-quality office products. Most often, modern chlorine-free bleaching technologies are used, which are more environmentally friendly and do not form dangerous organochlorine compounds. Chemical reagents, such as hydrogen peroxide, ozone, sodium dithionite, or oxygen, gradually oxidize or reduce the colored components, thus lightening the mass without destroying the fibers themselves. In general, this is a fine balance, as too aggressive bleaching can worsen the strength of the paper. In addition to bleaching, at this time, deep cleaning of the cellulose suspension from small impurities, residues of paint, metal particles, resins, which can affect the color and quality of the product, takes place. For this, flotation units are used, where impurities, due to the difference in specific gravity and surface properties, are separated from the mass and removed. After this treatment, the cellulose mass becomes light, clean, and homogeneous, ready for the next stage of forming thin paper sheets. The formation of a paper web is the moment when the cellulose mass, consisting of fibers and water, becomes the paper itself. The process takes place on special equipment, a paper-making machine that has a processing screen. The cellulose suspension is evenly distributed over a large metal screen, which continuously moves forward. Through the openings of the screen, water begins to drain down, reducing the moisture in the paper mass. The fibers, in turn, are retained and begin to form a thin but strong layer. This thin layer, the future sheet of paper, continuously moves together with the screen to a complex of presses and drying rollers. Here, the remaining water is finally squeezed out, the paper is heated, and acquires the required density and texture. After completing these stages, the thin and strong sheet of paper continues its journey to layer-by-layer processing and cutting. After forming a thin layer of cellulose mass, the process of pressing and drying begins. First, the paper sheet passes through the press section of the machine. Here, 2 or 3 heavy rollers press the thin layer, squeezing out the excess water. It's similar to wringing out a wet cloth. Pressing increases the density of the paper and prepares it for the next step. The moisture after the press is reduced to about 45%. Next, the sheet moves on to the drying rollers, large cylinders heated by steam, the temperature of which can reach 300 degrees Fahrenheit. The paper passes between these rollers, and the heat quickly evaporates the remaining moisture. The moisture exits through the open pores of the paper and drains into a condensate collection system. This stage is very dynamic. The paper sheet can move at a speed of several hundred meters per minute, quickly drying, but at the same time retaining its flexibility and strength. After drying, the paper becomes strong, smooth, and ready for further calibration and cutting. If necessary, the sheets pass through calendars, mounted pairs of rollers that give the paper a smooth shine and even thickness. After drying, the paper sheet passes through a pair of large, heavy, and very fast rotating steel rollers. This is called a calendar. These rollers press on the paper with great force, literally rolling it, to even out the thickness and give it a shiny surface. The temperature of the rollers can be very different depending on the type of paper, from about 80 degrees to over 500. The heat helps the fibers to melt a little, which improves the smoothness and strength of the web. With the help of calendaring, the paper becomes denser, more uniform in thickness, and also better suited for printing, as the ink lies on such a surface evenly and richly. The final stage of paper making is cutting and packaging. The finished paper roll, or a long ribbon, is fed to automatic cutting machines, where it is cut into sheets of standard or individual sizes, depending on the needs. For this, guillotines are used, large mechanical scissors that make an even and precise cut simultaneously across the entire width. Every year, humanity creates energy that on one hand saves cities, and on the other, hides an incredible story of transformations. One average reactor produces 1,000 megawatts and requires only 27 tons of enriched uranium per year, the weight of 3 school buses. But to get these 27 tons, you have to mine and process over 100,000 tons of ore. In this video, we will follow the path from a noisy mine and acid vats to supersonic centrifuges, furnaces, and tiny fuel pellets. Every step is chemistry, giant machines, and unexpected risks that you are almost never told about. Stay until the end, and I will reveal one secret to you that will change your perception of atomic energy. An average American nuclear reactor has a capacity of about 1,000 megawatts. For it to operate for 1 year, it needs approximately 27 tons of enriched uranium fuel. 27 tons is the weight of about 3 school buses. And now let's compare. To produce the same amount of electricity, a coal-fired power plant needs to burn over 3 million tons of coal. That's over 10 million barrels of oil. Nuclear fuel is the highest form of energy concentration that humanity has ever created. But to get these 27 tons of fuel, you need to start with a much, much larger amount of raw material. The chain of transformations is simply staggering. To produce those same 27 tons of enriched uranium fuel, you need to start with 215 tons of uranium concentrate. And to get those 215 tons of concentrate, you need to mine and process over 100,000 tons of uranium ore. Imagine a giant mountain of stone, the size of a multi-story building, which ultimately turns into a volume of fuel that fits in one truck. This shows how dispersed uranium is in nature and how complex the process of its concentration is. It all begins in the roaring chaos of a uranium mine. Imagine a deep shaft or a giant open-pit quarry, where huge machines with a deafening roar bite into the rock. The air here is thick with dust, and every stone that is brought to the surface looks absolutely ordinary, just a gray, dull granite or sandstone. The uranium here is invisible. It is dispersed in the rock in the form of tiny microscopic inclusions, and its concentration is incredibly low, often less than 1%. This means that to get 1 pound of uranium, you need to mine and process hundreds or even thousands of pounds of barren rock. Dump trucks, loaded to the brim, take this ore to a nearby processing plant that hums. The first stop is the primary crusher. This is a giant steel maw that, with a deafening crunch, crushes large stone blocks into pieces the size of a fist. Then, this crushed stone goes by conveyor to a huge mill. A giant rotating drum, filled with steel balls, resembles an industrial washing machine for stones. Here, in a continuous roar, the ore is ground into the finest grey sand, almost dust. And now the real chemistry begins, a process called leaching. This grey sand is mixed with water, forming a thick pulp, and pumped into huge vats, the size of a small house. A powerful chemical solvent is added to these vats, most often sulfuric acid. This acid, like a hungry predator, begins to eat the uranium, pulling it out of the solid rock and turning it into a liquid, dissolved state. This process lasts for many hours, while the entire mixture is continuously stirred. As a result, we get two things. On one hand, tons of wet, now unnecessary sand, so-called tailings, which are toxic waste, and on the other, a murky, greenish-yellow liquid containing our precious uranium. This liquid needs to be cleaned and concentrated. It is passed through a series of columns filled with special ion exchange resins. Imagine this as a high-tech water filter. The resins, like a magnet, pull out only the uranium ions from the solution, letting everything else pass by. Then these resins are washed with another solution, which washes the concentrated uranium off them. And so, finally, our final product is precipitated from this clean, saturated liquid. By adding ammonia or hydrogen peroxide, the uranium is forced to fall out of the solution in the form of a bright yellow, thick precipitate. This precipitate is filtered, dried in furnaces, and at the output, we get the same famous yellow cake, a heavy, radioactive, mustard-like powder. This is the uranium oxide concentrate, the first step on the long path to clean energy. The next step is purification to an absolute, almost unearthly purity. The yellow cake is sent to a special plant, where it is dissolved and, with the help of complex chemical processes, such as solvent extraction, all impurities are removed from it. The goal is to obtain perfectly pure uranium dioxide. But here the main problem arises, which is at the heart of all nuclear energy. In this perfectly pure uranium, 99.3% is the stable, lazy isotope uranium-238, which cannot sustain a chain reaction. And only 0.7% is the energetic, unstable isotope uranium-235, which is our fuel. They are chemical twins, and it is impossible to separate them by chemistry. To make the reactor work, we need to increase the concentration of this energetic uranium-235 from 0.7% to 3 or 5%. To begin enrichment, the solid uranium must be converted into a gas. It is treated with hydrofluoric acid, turning it into uranium tetrafluoride, and then with fluorine to obtain uranium hexafluoride. This is a very corrosive and dangerous compound, which has a unique property. It becomes a gas at a temperature slightly above room temperature, and so this gas, packed in special containers, is sent to an enrichment plant. Imagine a giant, noisy workshop the size of several football fields, filled with thousands of identical, tall, metal column-like devices. These are gas centrifuges. Each of them is a high-tech top that rotates at supersonic speed, making tens of thousands of revolutions per minute. When our uranium gas is pumped inside, the magic of physics begins. The heavier gas molecules with uranium-238, under the action of centrifugal force, are pressed against the walls of the centrifuge, and the very slightly lighter molecules with uranium-235 remain closer to the center. This is a microscopic difference, but it is enough. Special tubes take the gas from the center, which now contains a little more uranium-235, and send it to the next centrifuge in the cascade. And the depleted gas from the walls is diverted to the side. To achieve the required concentration of 3 or 5%, the gas must pass through thousands of such centrifuges. This is an incredibly long and energy-intensive process. When we have finally obtained our uranium hexafluoride, enriched to the required level, it needs to be converted back into a solid material suitable for fuel. With the help of chemical reactions, it is turned into a black powder of uranium dioxide. But this is not just any powder. Each of its particles has a perfectly calibrated size and shape. Now the most interesting part begins, the creation of fuel pellets. This black, heavy powder is sent to a press. Imagine a high-precision pharmaceutical press, only instead of medicine, it stamps radioactive pellets. It compresses the powder with incredible force, turning it into small, dense, perfectly cylindrical granules, or pellets. They are still brittle, like chalk. To give them strength, they are sent to a furnace. But this is not an ordinary furnace. This is a high-temperature furnace, filled with hydrogen to prevent oxidation. There, at a temperature of over 3,000 degrees Fahrenheit, these pellets are baked for many hours. During this process, called sintering, the powder particles fuse together, and the pellet turns into an extremely hard, dense, ceramic-like substance. It becomes so strong that it can withstand the extreme temperatures and pressures inside a nuclear reactor. Each pellet after this undergoes laser control, which checks its dimensions with micron accuracy. The next step is assembly. These small black ceramic candies are carefully, one by one, loaded into long, thin tubes. These tubes, about 13 feet long, are not made of steel, but of a special zirconium alloy called zircalloy. This material is unique in that it is very strong, resistant to corrosion, and most importantly, almost transparent to neutrons, allowing the chain reaction to proceed without hindrance. When the tube is completely filled with pellets, it is filled with an inert gas, usually helium, to improve heat transfer, and hermetically sealed at both ends. Now, it is not just a tube with pellets, it is a fuel element. And the final stage is the creation of a fuel assembly. Several hundred such ready-made fuel elements, for example 17 by 17, which gives a total of 289 pieces, are assembled into one large square bundle. They are held together by special spacer grids. This ready-made assembly, which looks like a giant, high-tech quiver with arrows, is the final product. It weighs about half a ton and is ready for shipment to a nuclear power plant. And so, having passed an incredibly long and complex path from an ordinary stone through chemical transformations, supersonic rotation in centrifuges, infernal baking, and precise, almost clockwork assembly, this concentrated bundle of energy is born, ready to quietly and reliably produce millions of kilowatts of clean electricity for several years. Every year, over 50 million tons of batteries are discarded worldwide, from small AA batteries to giant electric vehicle batteries. Imagine a mountain of metal reaching the size of Mount Everest, filled with toxic substances. But now, part of this mountain gets a second life. Behind the thick walls of factories, old batteries are put into shredders where steel blades tear them apart. They are frozen with liquid nitrogen and turned into a black powder that will once again become lithium or cobalt. Watch until the end. You will see how a new future for energy is born from waste. Battery collection starts with people. Private individuals turn in batteries from phones and laptops. Car service centers, batteries from electric vehicles, and also businesses that use a lot of equipment. Collection points are in electronics stores, supermarkets, or specialized collection centers. Here, everything is as manual as possible. People bring batteries, and staff or volunteers accept and record them. Old batteries from factories or car service centers are delivered by trucks to large collection centers. Special battery containers have sensors that determine the fill level. When a container is almost full, a signal is sent to the collection company. Some companies use drones to check the fill level of large containers in remote locations. Batteries are sorted by type by people and machines, because batteries come in different types: lithium-ion, nickel metal hydride, lead acid, and so on. They cannot be mixed during recycling. At small collection points, for example, in cities, batteries are sorted manually by workers. They rely on markings, labels, and appearance such as shape and case color. Small batteries from smartphones or laptops go in one direction, and large batteries from electric vehicles in another. At large enterprises, automatic sorting lines are in operation. Machines scan batteries by size, weight, and the type of metals they contain. X-ray analysis or spectroscopy is used to determine exactly which battery is in front of the machine. After scanning, the batteries move along a conveyor to different bins, where they await the next stage. Even at automated factories, people are present. Operators check whether the machines are sorting the batteries correctly. If a problem arises, for example, a torn battery case or a missing label, people intervene and sort manually. Batteries from electric vehicles or solar stations are too large for automatic lines. This is where robots come into play, helping to disassemble these giant blocks into smaller sections. Then they are sorted by material. No matter how much machines do, people are still the most important in the sorting process. These are mainly the workers at collection points and the operators of sorting lines. Specialists assess damaged batteries manually because machines cannot yet recognize all defects. Machines work faster, but for now, they can't do without people. Ultimately, every correctly sorted battery is a chance to recover rare earth metals and reduce environmental harm. Next, the batteries need to be shredded. They enter real metal jaws. The batteries are loaded into a machine that looks like a huge shredder, equipped with steel blades. The blades are so powerful that they can even shred the body of an electric car. Metal chaos ensues. The sound of tearing, grinding, and cracking. The batteries are literally ripped to shreds. Since the batteries can be charged, they first undergo freezing in liquid nitrogen. This cools the metals and reduces the risk of ignition. Some shredders operate in sealed chambers with inert gases to exclude contact with oxygen. There is also a more spectacular option. In some places, a controlled current is first used for ignition. The battery literally burns out, leaving only the metals. The batteries are shredded into pieces from a few centimeters to a crumb, depending on the type of shredder. The blades rotate at a speed of over 2,000 revolutions per minute, and metal fragments fly in all directions with a clang inside a protected chamber. The shredded pieces pass through magnetic separators, which, with filigree precision, extract ferromagnetic metals, for example, nickel or cobalt. Fragments of other materials continue their journey along the conveyor. A fine black powder, known as black mass, settles in special containers. This is where the treasures are hidden: lithium, cobalt, manganese. Machines literally suck up the powder with dust collectors to gather even the microparticles. Residues that are not suitable for recycling, meaning plastic and traces of electrolytes, are washed away with special streams of liquid. At this stage, hydraulic crushers are used, which turn the remnants into a slurry that is easy to filter. Engineers monitor the condition of the shredders and the temperature level inside the chambers. Specialists work with the results of the shredding. They check whether all the metals have been separated and whether any extra impurities remain. If a battery is charged and has defects, it can literally explode during shredding. But the system controls this. The explosion is extinguished by gases, and the process does not stop. After the batteries are shredded and that precious black powder is obtained, science in action, as they say, begins. The metals that seem to be hidden forever are extracted using two main methods: hydrometallurgy and pyrometallurgy. And although this may sound a bit technical, the processes themselves are extremely interesting. So what does it look like? Battery fragments are immersed in special acid solutions. There are huge tanks where a yellowish-green liquid is bubbling. This could be sulfuric or hydrochloric acid. During immersion, a reaction occurs. Lithium, cobalt, nickel, and other metals literally dissolve in this soup. To extract the desired metal, a clever trick is used: ion extraction. Special reagents, for example, organic compounds, are added to the liquid, which capture a specific metal, like a magnet. As a result, each metal settles into a separate layer. When the metals are separated, they are precipitated in the form of salts or hydroxides. They look like small white or colored crystals. For example, lithium precipitates as lithium carbonate, a powder that looks like fine sugar. Cobalt becomes a bright blue precipitate, and nickel, a pale green one. If hydrometallurgy is a gentle approach, then pyrometallurgy is more like shock therapy for metals. Here, everything literally burns and melts. The black mass is loaded into a huge arc furnace, where the temperature reaches almost 3,000 degrees Fahrenheit. The metals melt into a liquid mass, and the plastic and other residues simply burn up. The metals stratify like oil and water, but at the temperature of molten lava. Several layers form in the furnace. Heavy metals, meaning cobalt and nickel, settle to the bottom, while lithium remains in the slag. This is the upper, lighter layer. Then this slag is broken up and processed separately to extract the lithium. After cooling, the metals take the form of small ingots, shiny, smooth, and ready for reuse. The cooling after the pyrometallurgical process usually happens in a controlled manner. After all, if you just let the molten metals cool on their own, it could take hours and sometimes even days. In addition, such cooling can create an uneven metal structure. This will affect the quality of the final product. Therefore, they are usually cooled in special chambers, where the cooling rate can be regulated. If the controlled cooling is air-based, the ingots are left on a conveyor under powerful fans. It's like a giant hairdryer that quickly cools the metal surface. If it's water cooling, for a faster process, the metal ingots can be immersed in a bath of water or special liquids. This is a huge tank where the red-hot ingot, upon entering the water, releases clouds of steam. It looks quite spectacular. Sometimes there is combined cooling. This is when some stages begin with air cooling and then are completed with water cooling to reduce stress in the metal. Controlled cooling ensures a uniform structure of the metals, which is critically important for their reuse in batteries. This reduces cracks or defects that can arise from sharp temperature changes. The obtained lithium is used to create new batteries, those that will charge electric cars or even your phones. Nickel can become part of turbines that generate energy from wind, and cobalt, an important component of medical equipment. So we are literally closing the loop. Old batteries give life to new technologies. Discarded batteries can turn into a real environmental disaster. First, they contain toxic substances that pollute the soil and water. Second, the mining of new rare earth metals not only depletes natural resources, but also harms the environment. Recycling solves both of these problems. You know what else is cool? The more batteries we recycle, the less we depend on mining new materials. This is a direct path to sustainable development. Despite the popularity of lithium, only 1% of this metal is currently recycled. The main reason is the high cost and complexity of the process. But researchers are developing new technologies that could change the situation in the coming years. Interestingly, even now, electric car manufacturers like Tesla, Volkswagen, and BMW are investing in their own recycling plants to maintain control over valuable materials.